Hello everyone, and today we have a fun little probability question from Morphocular. If we have two random variables on the interval 0 to 1, x and y, what's the probability that when we round x divided by y, the result is even? Now, this seems like a pretty simple question on the surface, but the odds aren't actually 50-50 as you might expect. So let's go ahead and investigate. Since we're rounding x and y and it has to be positive, this means that the result right here is going to be an integer. So it can either be 0, 1, 2, 3, and so on and so forth. And say the result is 0, right? What does that tell us about x and y? Well, since we're rounding x and y, what this tells us is that x over y has to be less than 1/2. Otherwise, it just wouldn't round to 0. Okay, cool. If we round x over y and the result is 1, what does that tell us? Well, that tells us that x over y has to be in between two things, namely between 1/2 and 3/2. And for 2, it's something similar. X over y has to be greater than 3/2, but less than 5/2. And in general, if I'm just going to change this 3 to an n, this 3 becomes an n. In general, we're going to have 2n minus 1 over 2 has to be greater than or equal to x over y, which has to be less than 2n plus 1 on 2. In general, once you apply the base case, this general rule right here does apply. So now we can simplify the question a little bit. Instead of asking what the probability of round x on y is, and that being even, what we can instead ask is what's the probability that x over y is less than 1/2, or in between 3/2 and 5/2, and so on and so forth for every single even number. But this begs the question, what exactly is the probability that x on y is less than or equal to just some, I don't know, call it alpha? What is this right here? Because in order to answer this question right here, we need to find this right here. We need to find the CDF for x on y. So let's go ahead and do that. The way we can find the probability distribution function for these two variables right here is actually to consider what happens when one of the variables is quote-unquote constant and we just integrate over it. So what I mean by that is we can express this expression right here as the probability of x on y being less than or equal to some alpha, given that y is equal to just some capital Y, some number. And then what we can do then is just integrate this expression right here over the distribution for y itself. So fy right here being the cumulative distribution function for y. But this right here isn't exactly a very nice expression, and we can simplify it quite a bit. This differential right here we can rewrite as this right here. Change the differential, and whenever we differentiate a cumulative distribution function, we're just going to get the point distribution function. So in fact, this integral right here is really just the integral of this probability, so the probability that x on y, but since y is constant in this case, I'm just going to go ahead and move it over to the other side, so that way we have our variable on the left and all just constants on the right. So we have the probability that x is less than alpha y, and then times the point distribution function for y, and then we're integrating with respect to y. But what exactly is the point distribution function for y? Well, that's just going to be 1. It is the uniform distribution over the interval 0 to 1. So it is literally just 1. So boop, that's just 1. You can ignore it for all intents and purposes. So now this begs the question, what exactly is this right here, the probability that x is less than or equal to alpha y? Well, we already said that y right here is just some number. And in fact, I probably should have written it like this. The probability that x is less than or equal to some alpha capital Y. What exactly is this? Well, x is a random variable, but alpha y is just a constant. So what this really is right here is the cumulative distribution function of x. So this is just f sub x of, well, alpha y. But what in general is the cumulative distribution function for x? Well, this right here is actually a relatively simple question to answer, because we know that x is just a uniform distribution over 0 to 1. So f sub x of some x right here is just going to be equal to x if 0 is less than or equal to x, which is less than or equal to 1. And it's just going to be 1 if x is greater than 1. And it's 0 otherwise, but you don't really have to worry about that because y is the same distribution as x, so we're not going to really be integrating over any areas where this right here is 0. But it is technically 0 for negative values, etc. So since our cumulative distribution function right here is not continuous, this begs the question of what exactly is our argument right here? Is it going to be greater than 1 or is it going to be less than 1? And the answer actually is that it's both, depending on what alpha is. Because remember, we said x on y has to be less than or equal to alpha. But x and y are both going from 0 to 1. So if I pick x being like 0.25 and y being 0.999, obviously that right there is going to be alpha is just going to be less than 1. But I could very well choose the inverse of that. I just swap x and y in that case, and you're going to get something that approximates 1 over 0.25, which is just 4. So really, x on y can be any number between 0 and infinity, meaning that we're going to have two cases. One in which alpha is going to be less than 1, and the second case in which alpha is going to be greater than 1. Now let's go ahead and consider the second case first, where alpha is greater than 1. Well, if alpha is greater than 1, when we consider our integral, which is from 0 to 1 of f sub x of alpha y dy, since alpha is always greater than 1, we need to split up this integral right here into two regions. We need to split it up into the region where y goes from 0 to 1 over alpha of fx alpha y dy, and then into the region from 1 on alpha to 1 of the exact same thing. So f sub x of alpha y. In this first region right here, where y goes from 0 to 1 on alpha, the argument right here is always going to be less than 1. And the reason for that is because, let y be 1 over 2 alpha. Well, alpha times 1 over 2 alpha is just going to be 1/2. So in general, this right here, this argument right here, is always going to be less than or equal to, in the case of 1 over alpha, 1. But for this other region right here, what we're going to have, since y goes from 1 over alpha all the way to 1, what we're going to have is that this right here is going to be less than or equal to 1. So in this case, right here, well, since the argument is always greater than or equal to 1, this right here is actually equivalent to just integrating, by definition of this right here, of integrating just 1. So we have the integral from 1 on alpha to 1, just dy. But on this other side right here, we just have f sub x equaling x on this region. So we're integrating from 0 to 1 on alpha y dy itself. And we need to add those two together. Now these integrals right here really aren't too bad. We really just have alpha on 2 and then times 1 on alpha squared. And then we're just going to add 1 minus 1 on alpha. But this right here, whenever we simplify it, so, canceling things right here, we end up getting 1 minus 1 on alpha, and then plus 1 on 2 alpha, but that right there is just going to be 1 minus 1 on 2 alpha. So that right there is going to be our cumulative distribution function for alpha being greater than or equal to 1. So now let's go over here and consider the case when alpha is less than 1. Well, in this case, whenever we consider the integral from 0 to 1 of f sub x alpha y, well, in this case right here, here's the interesting thing. Alpha is less than 1, but y is also, by definition, less than, or I guess suppose equal to 1. It's in between 0 and 1. So this expression right here can never exceed 1. So we have the integral from 0 to 1 of just alpha y and then dy, which is just equal to alpha on 2. So now we have our CDF for x on y. Combining these two parts together, what we have for the probability of x on y being less than or equal to some alpha is just the following. If alpha is less than or equal to 1, then the probability is just alpha on 2, or the cumulative probability is alpha on 2. But if alpha is greater than or equal to 1, we have 1 minus 1 over 2 alpha. It should be noted that this probability function right here is piecewise, but it is continuous and continuously differentiable, because you'll notice if we plug in 1 for both of these right here, well, we end up getting 1/2 for both. And if you differentiate both of them, we actually do end up getting 1/2 for both of them still. So in fact, even though this is a piecewise function, it is a valid CDF. So now that we have the probability, let's go ahead and actually solve the problem we started with. To solve this original problem, what we're going to do is consider the base case first right here, because that one really is an odd one out, and then we're going to go into evaluating the nth case. So first and foremost, what is the probability that x on y is less than 1/2? Well, since 1/2, I should really write the CDF right here. Okay, now what's the probability that x on y is less than 1/2? Well, if we just use this right here, it's just a fourth. Bada bing, bada boom. It's as simple as that. Now, what about any even number? Because if you remember, if we want this round of x on y to be even, we need this n right here to also be even. And we can just kind of check this quite quickly. For example, this 2 right here, if you plug in 2 here, we end up getting something in between 3/2 and 5/2. The only integer between 3/2 and 5/2 is indeed 2. Do that for 4, we end up getting 8 minus 1, 7 over 2, something in between 3.5 and 4.5. That right there is just 4. What we need to find then, in general, is just going to be the probability of some 4k minus 1 over 2 being less than or equal to x on y, which is less than 4k plus 1 on 2. So how exactly do we find this? Well, we can split it up into two ways. We can say that this right here is the probability that x on y is less than 4k plus 1 on 2, and then just minus the probability that x on y is less than 4k minus 1 over 2. So let's go ahead and use our CDF right here to figure this out. Because our alpha is going to be greater than 1, we are just going to be using this right here. So for the following section, we're just going to have 1 minus 1 over 2 alpha right here, which means that for this, we're just going to have 1 minus 1 over 4k plus 1, and then minus 1 minus 1 over 4k minus 1. And this right here simplifies quite nicely into just being 1 over 4k minus 1, and then minus 1 over 4k plus 1. Now, you might be thinking, oh, well, we can just use a simple summation trick, because we need to sum this for every single possible even number. But in this case, because these right here are 4s, it's not actually possible to simply reindex the sum and then cancel out all the rest of the terms, like you might do for, say, 2k minus 1 and 2k plus 1. Instead, we're going to have to resort to other techniques to evaluate the summation, namely, my favorite, complex analysis. So what we have then is the sum from k equals 1 to infinity. Gotta love when infinite sum comes into play. Of 4k minus 1, and then minus 1 over 4k plus 1. Multiplying the top and bottom by the appropriate thing, we end up getting the sum from k equals 1 to infinity. I understand the appropriate thing is rather vague, but just multiply each by the quote-unquote conjugate, right? So multiply this by 4k plus 1, multiply this by 4k minus 1, the top and bottom, obviously. And what you end up getting is 2 over 16k squared minus 1. And what's nice about this, actually, is it's symmetrical. So if we make k negative, we end up with the exact same thing as if k was positive. This means that we can actually express this sum right here as 2 times the sum from k equals negative infinity to infinity of, or sorry, 1/2. 1/2 the sum from k equals negative infinity to infinity of 16k squared and then minus 1. Now here we are double counting the case k equals 0, so what we need to do is subtract 1/2, and then whatever k of 0 is of this expression, which happens to be -2. So this whole thing right here is just going to be plus 1. Okay, so now all we have to do is evaluate this sum right here, and just note that the 2's cancel, which actually isn't so bad. We know that from complex analysis, this right here is just going to be -pi times the sum of the residues of, well, cotangent of pi z over 16k squared, and then minus 1. So what exactly are the poles of this right here? Well, we're going to have poles at, I realize I'm mixing k and z. Whoops. Not going to change the location of our poles though. We're gonna have poles at z equals plus or minus 1/4. So this right here is going to be, and they're both simple poles, so this really isn't too bad. What we're going to have is just, well, let's consider the case z, or the pole z equals 1/4 first. This means that we're going to have cotangent of pi on 4, and then just divided by, well, since we can factor this right here into 16, and then times z plus 1/4, and then z minus 1/4. Since we can do that, the denominator here is just going to be 16, and then times, well, this right here is going to cancel. So what we're left with is just going to be times 2 over 4. And then similarly on for the next residue, so for z equals -1/4, we're just going to have the cotangent of, well, minus pi on 4, and then over 16, and then times just -2 over 4. Thankfully, though, the minus signs do cancel, and we're left with this expression right here, which can be evaluated relatively simply, just moving on down here. What we're going to have, move everything with the denominator over to the pi, right? So 16 times 1/2 is just going to be an 1/8, so we have pi on 8. But then we're just going to have 2 times cotangent of pi on 4. But cotangent of pi on 4 is just 1, so really we just have pi on 4. Or sorry, minus all that, so minus pi on 4. So, what do we have all in all? Well, the probability that if we have x and y distributed over the interval 0 to 1 uniformly, we round that, the probability that it is 0 is just going to be 1/4, right, as we said right here. But we also know that the probability that it is any other even integer that's greater than 0, we know that to be the result of this sum right here, which is just 1 minus pi on 4. Now, when we add both of these things together, the whole result is just going to be equal to 1/4 and then plus 1 minus pi on 4. Or, to write it nicely, we can just have 5 minus pi on 4. And that right there is the answer. I hope you enjoyed this video. A little bit of a different one, but I had a great deal of fun doing this. Thank you to Mofocular for this fun little problem, and I will see you in the next one.